Hello everybody and welcome back to Prospect Charter School's Algebra 1 class. Today we're going over section 1.7, which is simplifying expressions. To simplify expressions, we are first going to go over some of the properties of real numbers. We're going to go over what terms are, what like terms are, the distributive property, the commutative property, the associative property, and then a few examples. So here we go, starting with our definitions, because if we don't know what our definitions are, then we don't know what we're talking about, and nobody wants to not know what they're talking about. Well, maybe some people do, but that's just kind of wrong. You really should know what you're talking about. So here we go. Here is our first definition. Our first definition is the commutative property. Now, the commutative property is the property that allows us to move around. The key word here is commute. For an example, Mr. O'Neill commutes to work from Shady Cove to Prospect every day. So, the commutative property allows us to move numbers around. An example would be something like 2 plus 7 is equal to 7 plus 2. Or 4 times 5 is equal to 5 times 4. These are examples of the commutative property. Algebraically, we would say A plus B is equal to B plus A, or A times B is equal to B times A, meaning that if I take the A and I move it to the other side, it commuted, it moved. Just like on this one, if I took the B and moved it to the other side, it commuted or moved. So the commutative property says that you may, if I can draw a good Y, you may move numbers of the same operation. So what does it mean to be an operation? An operation is addition or multiplication. So we can move addition, we can move multiplication. So one more example, what about something like 4 minus 3? Oh, we said it could only be with addition or multiplication, but this is subtraction. Well, as we know from a previous lesson, this is really for plus negative 3. In which case, again, you can commute. You can have the negative 3 move to the other side of the 4, or the 4 move to the other side of the negative 3. Doesn't really matter which way you think about it, because in the end, you end up with negative 3 plus 4 at the end. So we can use the commutative property to move numbers around so that we can get things to be associated with each other, which brings us to the next property, which is the associative property. Now, the best way to explain the associative property is with an example from school. I know you guys like to chat. I know you guys like to chat a lot. In fact, you like to chat too much. But such is life. An example would be, let's say that we have two girls chatting away, and they're supposed to be facing forward, but of course they're not. So these two are associating with each other. Well, in front of those two girls is a guy who also wants to be associated with them, but he doesn't know how to do that. He especially wants to be associated with the girl in the middle because she's cute in his opinion. So what does he do? That's right, he goes to the gym and he gets mega buff. So let's show the mega buff guy from working out at the gym. Not to mention he grew like 6 inches. And then suddenly, instead of associating with the girl behind her, she realizes that there's a hot guy in front of her. So what does she do? Yeah, she stops associating with the girl behind her and then starts talking to the hot guy in front. So these two start to associate with each other. And the girl in the back starts getting depressed because she's kind of left out. But it happens. Such is life. Now, what does this have to do with numbers? Well, it's the same thing. The numbers allow you to associate different numbers of the same operation. So for the associative property, a numerical example would be something like 4 plus 2 and then minus 3. Now, if you'll notice, these two are associated with each other, just like in the example above that the girl in the middle and the girl in the back were associating with each other. But if I wanted to, I could remove that association, and instead of having it as 4 plus 2 minus 3, turn it into 4 on the outside of 2 minus 3. Suddenly, the girl in the middle went from associating with the person behind them to associating with the person in front of them. Note that the order didn't change. Changing order would be a commutative property thing. Associative property only deals with who you're dealing with. So when we are doing the associative property, it is that you may perform operations of the same kind in any order. So an example we had here was all addition. And we could do the same example with all multiplication. We could do 4 times 2 times negative 3, which would be equivalent to 4 times 2 times negative 3. Both of those are identical because we can use the associative property. After the associative property is the most important of them. It is called the distributive property. Now, in the previous examples, we had distributive. We had everything had to be the same operation. Multiplication hung out with multiplication. Addition hung out with addition. And never the twain mixed. Well, the distributive property is the happy marriage between addition and multiplication. So here is our happy bride in her beautiful dress with her flowers, which looks more like an ice cream cone, but oh well. And then multiplication would be the happy groom with his bow tie on, ready to go, right? Distributive property is the happy marriage between both addition and multiplication. It allows us to have them work together in ways that make life a lot easier, especially when we're dealing with algebraic expressions. So let's give an example of distributive property and then try to put it into words. Let's say that I have A and it's being multiplied by the quantity B plus C. And right now you're all scratching your head saying, Mr. O'Neill, why do you start with the hardest one? And I say because it's the most general case. In this situation, the most general case is that we can take our A and we can distribute it to the B and the C. So it becomes A times B, which is AB, plus A times C, which is AC. Now I know that doesn't make very much sense to you guys, so let's do another example. Let's look at 3 times x plus 2. And again, this is a complicated situation because we have a variable. We don't know what the value of x is. It could be anything. It could be 2, it could be pi, it could be e, we don't know. So when we're working with these, we would have to use the distributive property to possibly be able to solve for x. So to do that, we would distribute the 3 this time instead of the a to both the x and the 2. And when we do that, we would say 3 times x is 3x. 3 times 2 is 6. So it becomes 3x plus 6. So the distributive property says that if you multiply across addition, And I probably misspelled across. Fortunately, I'm not an English teacher, so my utter lack of ability to spell is not too much of a hindrance. If you multiply across addition, the multiplier goes to all of the addition. I'm going to say to each term. And we'll go over what a term is in just a moment. So for an example, in the distributive property, we did the a times b plus c, and then we did the 3 times x plus 2. But how about one that's easier to make sense of? One that just deals with pure numbers. Well, to do that, let's get the example up and running. Let's say we have 3 times 4 plus 2. Now, if we use the order of operations, we would of course go 4 plus 2 is 6, and then 3 times 6 is 18. But we want to prove that the distributive property works. So our first thing would be to multiply or distribute the 3 to each piece, in which case we get 3 times 4, which is 12, plus 3 times 2, which is 6. And 12 plus 6 is also 18. So obviously the distributive property still works. It should. It should always work. In fact, that's why in some classes it's actually called the distributive law, but we're here in Algebra 1, we don't need to know about laws, we need to know about properties. Speaking of, I have some beachfront property for sale. It happens to be in Arizona if anybody wants to purchase it. Alrighty then. Next up, we have the term and like terms. These definitions are kind of important because if we don't know what terms and coefficients are, we're going to be in big trouble. So our first one is the term. A term is a variable and its associated coefficient. So yeah, do we know what coefficient is? Not really. Do we know what variable is? Well, kind of. So an example is worth 1,000 pictures or 1,000,000 words. So let's go ahead and do our example. Let's say that we have the term 4x. The 4 portion is called the coefficient. The coefficient is always a number. We might not know what that number is, but we know that it is a static number. It always remains the same, always. It never changes. Otherwise, it would be called a variable. Because what is that other piece called? That's right, that's the variable. Because we don't know its value, and it can change. For an example, time changes all the time. What time is it right now? Well, according to my clock, it's 8:12. So, is it going to stay at 8:12? Well, I guarantee that by the end of the video, this will not say 8:12. So the variable, like time, changes. The coefficient remains static. So that brings up like terms. What are like terms? Well, like terms are terms with the exact same variable. So this one throws a wrench in the works because the variable has to be exactly the same for them to be like terms. So let's do some examples and determine if they are like terms. Example A, 4x and 2y. Are these like terms? The answer to that question is no. X and y are not the same exact letter, therefore they are not like terms. Okay, so put a big X there. What about 2y and 2x. These could be the same. Well, once again, we're looking at the variable. We don't care about the coefficients. We only care about the variables for things to be like terms. So since these do not have like terms or the same variable, they are not like terms. All right, let's try another one. Let's try 4x and 4x squared. Aha, you might say. These must be like terms. Look, they both have x's. Yay! They are not like terms. What do you mean they're not like terms? Well, when it says the exact same variable, they mean the variable and its power. So in the first one, we have a power of 1, which is invisible. In the second one, we have a power of 2. So is 2 the same thing as 1? No. So these are not like terms. By now you're getting a little frustrated, probably wondering, what exactly are like terms? Give me some like terms. I'm like, okay. All right, calm down. Calm down. How about 2x and 1/2 x? Well, x is the exact same thing as x, so yep, these are like terms. And last but not least, let's try some really complicated variables. Let's look at 4xy versus 2yz. Are these like terms? You might be tempted to say yes, because, hey look, they both have y in them, so obviously they're like terms. No, they are not. The reason being is that we have an x and we have a z, and x and z are not the same thing. So the variable in this case is not just one letter, but two. It's the x and the y put together, just like this one's variable is the y and the z put together. Because of that, they're not like terms. But what if we had something like 4xy and 21xy? Well, the variables are the exact same thing in both cases, xy and xy, so these would be like terms. All right, time to do some examples. Let's consider some easy ones first. Let's look at combining like terms. In this case, let's look at 2x plus 4x. Now, are they like terms? So yes, they are. They are like terms. So we'll put over here like terms. So we can combine them. You cannot combine unlike terms. They have to be the exact same thing. They have to be like terms for us to be able to do anything with them. Unless, of course, it's multiplication, which is weird. But with addition, if we want to be able to combine like terms, or if we want to be able to combine things, they have to be like terms. Is x the same thing as x? Yes, it is. So when we combine these, the coefficients change, but the variable remains the same. So let's write that as a note. When combining, the coefficients change, but the variable remains the same. This is really important because if we couldn't do this, a lot of algebra would break and we wouldn't be able to get very far in math at all. But because we can, we can combine the like terms of 2x and 4x. When we do that, our variable does not change. It stays as x, but our coefficients, the 2, if I can circle the 2 and the 4 can combine. 2 plus 4 is 6, and then the variable remains the same. So we have 6x. Let's do another one, just so that we understand how it works. What about 4x squared minus 2x squared? They're like terms. We combine the coefficients. 4 minus 2 is 2. The variable remains the same. What about 4y minus 2x? Well, they're not like terms, so we have to leave them as is. How about 3y squared minus 4y? Again, not like terms, so we can't really do anything. All right. Next set of examples. Let's take an example of looking at how we can use all of the properties that we have gone over and use them to simplify an expression. Our expression for today, this mega expression, is going to be 2 times the quantity, x plus 6, and quantity, plus 3x. Now, on this example, I'm going to do this example as formally as I possibly can. We are going to do this as if we are computers and don't know how to use our intuition. So our first step would probably be the distributive property. What we are going to do is we are going to distribute the 2 to the x and the 6. So it goes to the x and it goes to the 6. So when I do that, it becomes 2x, because 2 times x is 2x, and then 2 times 6 gives us 12. And that leaves the 3x hanging out. Next up, I want to combine like terms. But right now, because of my associatives, the way things are associated, the 2x and the 12 are associated, and they're not like terms, so I can't do anything. And then the 12 and the 3x are associated, but again, they're not like terms, so I can't do anything. So can you guess what we're going to do on the next line? I'll give you a hint. It deals with driving. I'm going to use the commutative property. And I'm going to move the 12 to the other side of the 3x. That will then allow me to associate the 2x and the 3x. So when I do the commutative property, the 12 moves, but everything else remains in place. So now I have 2x, the 12 has moved, so next would be the 3x, so plus 3x, and then finally the recently moved plus 12. Now I need to use the associative property to associate two of these together. So on my next line, I'm going to call it the associative property. And the associative property is going to let me say, all right, I want the 2x and the 3x to be combined, and we're going to leave the plus 12 all on its own. So when I do that, I can then combine like terms, and have 2x plus 3x. 2x plus 3x is 5x. And then we have the plus 12. Can we do anything else? Well, 5x and 12 are not like terms, so we are done. All right. This video is going way longer than I had hoped, so let's go ahead and give you one final example of what I would like to see when I say show you work. We're going to use the exact same one. We're going to do 2 times x plus 6 plus 3x. And this is what I would expect to see on your homework. If I tell you to show your work, I don't expect you to do what I did in the example above. What I do expect to see is probably at least 2 lines. I would like to see 2x plus 12 plus 3x because I wanted to see that you had distributed the 2 to both places correctly. And then after that line, if you did 5x plus 12, then I see that you had done the combined like terms correctly. And then you can box your answer. Compared to the previous one, this is a lot shorter, but compared to what some of you can do in your heads, I understand. I absolutely understand just how easy some of this stuff is. But you need to show it. You need to show me that you're doing the right thing. Because sometimes we make errors. If I see something like 2 on the outside of x plus 6 and then plus 3x, and then in the end I don't have 5x plus 12. For an example, let's say I did 2, alright, that's 5x, and then 6 plus 2 is 8. Bam. Well, that's not correct. The correct answer was 5x plus 12. We have 5x plus 8. We did something very silly. We did 2 times 6 being 8, which is the same thing as 2 plus 6. It happens all the time. So if I saw that and we were doing a test, this would be 100% wrong. I would be able to give you no credit. But if you did this and showed that this was 2x plus 8 plus 3x, then I'd be like, aha, I see what you did there. You did 2 times 6 gives you 8. Don't worry about it. This would be an arithmetic error. You'd probably lose like 1 point out of 5. So it's a lot less. So please show your work. If you don't show your work, you have no safety net. And it's a very high probability that you will make mistakes and you'll have full points taken off for silly mistakes like 1 plus 1 equals 11 or 4 times 3 is 7. It happens all the time. So please show your work. In the meantime, it's time for your homework. Please note that I do want you to show your work. If you do not show your work, you're doing it wrong. All right, so here we go. Shazam, show your work. Section 1.7 on page 49, numbers 3, 5, 11, 13, 17, 19, 21, 23, 25, 27, 29, 31, 33, 35, 39, 41, and 45. For those of you who have Twitter, you already know what the homework assignment is because it was tweeted several minutes ago. Congratulations, good luck, and have fun.